Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to continue with energy of reactions, and we're going to focus on Hess's law. So in my previous videos we talked about how you could calculate the delta H of a reaction or the enthalpy of a reaction in two different ways. We use the heats of formation to calculate the delta H of a reaction, the enthalpy of a reaction, or the heat of a reaction. And we also used bond energies. How can we, I showed you how you could use the average bond energies to calculate the heat of a reaction. So that's two different ways. So enthalpies of formation or heats of formation in order to calculate the heat of a reaction, as well as using average bond energies. In this video, I'm going to show you how you could do the same thing using Hess's law. So what is Hess's law? Hess's law, simply put, is regardless of whatever path you take, you still get to the same place. So if you're going to use the idea of cleaning your room, right? Someone might clean the room differently than another person, but the room gets clean nonetheless. Another example would be with regard to energy. So when we're talking about the heats of a reaction, we're talking about the changes in energy. So if we look at this diagram here, this diagram represents two different paths that could be taken in order to get from reactants to products. So one is like one step where you go directly from reactants to products, and you see the energy change here. Another pathway is where you might take multiple steps or a series of steps to get to your products. Maybe the reactants get changed into one thing and then into another thing and then into a third thing, and then finally gets turned into products. So either way, either path, the energy difference between reactants and products is the same. So it doesn't matter how you get there as long as you get there. And so the energy change doesn't depend on the pathway you take. And in some circles or in college classes, they'll bring up the word or the idea of state function, where a state function is basically a function that doesn't depend on the path you take to get from A to B, but just it just is based on the initial conditions and the final conditions. And so another example that might be helpful to understand this is think about when you're going up from the bottom floor or the ground floor in a hotel to like the 100th floor in the hotel. There's two ways you can do it. One way is to take the elevator. The second way is to take the stairs. So if we're thinking about our potential energy, remember, potential energy is the energy related to position, how far you are from a certain point. So let's take the ground, for example. So if you're on the ground, you have zero potential energy, but as you get higher from the ground, you're increasing your potential energy. Now, you can have two pathways to change your potential energy when you're at the hotel, right? So you could start at the ground floor, zero potential energy. You could take the stairs, right? You go up the stairs to the 100th floor, you're going to increase your potential energy. If you take the elevator, you're also going to increase your potential energy. Either way, the amount of potential energy you're gaining is the same. It does not matter what path you take, right? You're still going from ground to the 100th floor or the 100th story of the building. Okay, so same way. That's what Hess's law is saying with regard to reactions. The change in energy of reactants to products does not depend on the pathway you take, right? So when we're calculating the heat of a reaction, all we care about is the starting energy of our reactants and the final energy of our products and the difference between those two. So as long as your pathway gets you from one to the other, the difference is going to be the same. So that's what Hess's law says. So Hess's law is saying in going from a particular set of reactants to a particular set of products, the change in enthalpy, which is a fancy word for the heat of a reaction, the change of enthalpy is the same whether the reaction takes place in one step or a series of steps. So if we look at this diagram down here, you'll see I have a set of reactants and a set of products, right? So if my reactance is A plus 2B, and I want to get to 2D as my product, I could either do it as one step, right? And that would be my delta H3. Or I could do this in a series of steps. So here's two steps. So I could first change A and B to C. So that would be a delta H1. So a certain amount of energy that it takes to do that. And then second step, I can change C to 2D, and that would be my enthalpy for this step here, my delta H. Well, these two together give me this here. So I could either go directly there and get my delta H3, or I could do the two-step pathway here, and it amounts to the same thing. So delta H3, this part, is equal to this part plus this part. So if I add the steps together, I should get the same amount of energy difference between A plus 2B and 2D. So I hope this is clear, and I'm going to be going over some examples. But first, let's talk about some relationships between Hess's law and the equilibrium. The reactions. So how does this apply to equations when we're talking about delta H's of reactions and the equation of the reaction? So let's talk about that next. Okay, so here are some relationships. Here are some relationships involving delta H of a reaction and equations. So let's go over this. So first, if you multiply an equation, a chemical equation, by a factor or number, then you multiply the delta H of the reaction by that same factor or number. So the reason for this is because your enthalpy of reaction, or the heat of a reaction, is an extensive property. If you remember, extensive properties are properties that depend on the amount of the substance. For example, mass is an extensive property because the more substance you have, the more mass you have. Volume is an extensive property, right? So the more substance you have, the larger the volume, right? And that's as opposed to intensive properties that don't depend on how much you have. For example, density, right? No matter how much gold you have, the density of gold is still the same. So the delta H of a reaction, or the heat of a reaction, is an extensive property. So the more that that's going through the reaction, the more heat that's evolved or absorbed by the reaction. So the more substance you have, the more heat you have, right? So here's a couple of Here's an example. So here we have carbon plus oxygen gives us carbon dioxide, and the heat of that reaction is negative 393.5 kilojoules. If we double that, like if we multiply everything by 2, if we multiply the whole equation by 2, then we get 2 carbons plus 2 oxygen molecules gives us 2 carbon dioxide molecules. So in that same way, we double the heat of the reaction. So now the heat of this reaction is double the previous one. So 2 times negative 393.5 becomes negative 787.0 kilojoules. Okay, so that is an example of the first relationship. So if you, whatever number or factor you multiply your equation by, you multiply the heat of that reaction by that same multiplier or by the same number. The second one is if you reverse the reaction by flipping the side. So if you make the products the reactants and the reactants become products, you flip or reverse the reaction, then you change the sign of the delta H, or the heat of the reaction, to get the new delta H, or heat of the new reaction, right? So here's our original equation. So we have carbon plus oxygen gives us CO2. So this is our original equation. This reaction has a delta H of negative 393.5 again, right? But what if we flip it? So we put the carbon dioxide as a reactant, the carbon and oxygen are products. So we're reversing the reaction. So the heat of this reaction, the enthalpy of this reaction is going to be the same, but it's going to be the opposite sign. So we're going to change the sign. So it was a negative for this one. We reversed it. So now we change and reverse the sign. So it's positive. So negative becomes positive. Positive will become negative. So if this was positive, then this would be negative. So we're changing the sign. So if you reverse the reaction, you have to change the sign of the delta H. So if it's positive, you're going to change it to a negative. If it's negative, you're going to change it to a positive. And then finally, third, if you add reactions together to make one overall reaction, then you add the delta H's of those separate reactions to find and get the delta H of the resulting reaction you got after you added them together, right? So this is Hess's law. So that's number 3. And so I'm going to go over a couple of examples where I'm going to show you how this all works using Hess's law. So stay tuned. Okay, welcome back. So here is Hess's law example number 1. And so in this example, I'm going to show how you can use those relationships that I talked about just a moment ago, where if you reverse a reaction, you have to make sure you take the opposite sign of the delta H of your new reaction to get the delta H of your new reaction. If you multiply by a factor, then you have to multiply the delta H of the reaction by that same factor. And if you add the equations together, if you add reactions together to get a third reaction, then you add those delta H's together to get the delta H of that resulting equation. So let's get into this. So our problem here is to calculate the delta H of reaction for the combustion of methane, CH4, and here is the combustion reaction. So we want to find the delta H of this reaction, but what we're given are these 3 reactions here with their delta H's. So we need to figure out how we're going to use these to get this reaction here. So first thing you need to do is take one equation at a time and see whether or not the reactants and products fit with the reactants and products here. Are they on the same side or are they not on the same side? Are they multiplied by the same coefficients? Do you have the same coefficients? If not, then you're going to have to multiply. So let's take a look at number 1. So we'll notice here that we want methane. We want one methane molecule on the reactant side of our target equation. But you'll notice here that we have CH4 as a product. We don't want CH4 as a product. We want it as a reactant. So we're going to have to reverse this equation. So let's reverse this one. So we'll do CH4. So CH4 will be a product. And then carbon plus 2H2 will be a reactant. So we reversed the reaction. So that means we're going to have to take the opposite sign of this. So it's negative, so we're going to have to make that positive. So the delta H of this new reaction is going to be the positive of this. So this is going to be equal to a positive 74.80 kilojoules. Okay, so now we have one CH4 as a reactant, and we have CH4 as a reactant here. We have hydrogen and carbon here. We don't have hydrogen and carbon, so what we're looking for is that these will be eliminated or canceled out by the other 2 reactions. Okay, let's look at number 2 here. So it looks like we have CO2 as a product. We have one CO2 as a product here. We have one CO2 as a product here. So this is the way we want it. We don't need to do anything to this equation. So this one we'll put right here. So carbon plus oxygen is going to give us CO2. So this is the same. So I'm just going to put it down there. And so the delta H stays the same. So we didn't really do anything to this one. We didn't have to. So this is going to be negative 393.50 kilojoules. All right, now what about our third one? Now you'll notice here that I have water as a product here, and I have water as a product here. You'll notice that I have two waters here, but I only have one water here, right? So, and you'll also notice that I have a half of an oxygen here. I have one oxygen here, but I have two oxygens here. If I could multiply this by 2, then I would get another oxygen. So, and I would get my two waters. So I need to multiply this equation by 2. So then this equation is going to be 2H2 plus 2 times 1/2 is 1. That's going to be 1 oxygen, and that's going to give me 2 water. So 2H2O. And since I had to multiply this equation by 2, then I have to multiply this delta H by 2 as well to get the new delta H. So the new delta H of this reaction is going to be 2 times this, which is going to be negative 285.83 kilojoules. Okay, so I have my reactions now, and so now I can see if these are going to add up to this one. So I'm looking for things to cancel out. So notice I have carbon and I have hydrogen. I want those to cancel out. So whatever's on a product side and a reactant side should cancel out. So I have one carbon as a reactant here. So I have one carbon as a product there. So those can be eliminated. So this carbon will be eliminated or canceled out with that one. And I have two H2s here, but I also have two H2s here. So as a reactant and as a product. So those can be eliminated. And you'll see that I have on this side, I want CH4 and 2 oxygens. I have CH4. So I have CH4 here, and I have oxygen and oxygen. So CH4 and 2 oxygens on the reactant side. And I for the product side, I want CO2 and 2 waters. So I have 1 CO2 here, and I have 2 waters there. Everything else cancels out. So when I add these 3 equations together, I get my resulting equation. So I get CH4 plus 2O2 yields CO2 plus 2H2O. So these 3 equations will add up to my resulting equation, my target equation. So that means that these 3 delta H's added together will equal the delta H of this resultant reaction, which is going to be, what did I calculate? I calculated this to be negative 890. Oops. Sorry about that. Light went off. So negative 890.36 kilojoules of energy. So that is the delta H of the combustion of methane. Okay, that's example number 1. Let's go on to example number 2. Okay, so here is our Hess Law example number 2. So example problem number 2, here they're giving us our target reaction. 2 NOCl gas goes to nitrogen gas, N2 gas, oxygen gas, and chlorine gas. And so they want to know what the delta H of this reaction is. and we're given these two reactions to work with. So again, we're going to look at whether the products and reactants here, make sure these are on the proper side according to our target. So let's look at reaction number one. So reaction number one, you'll notice that I have N2 and O2 gas as reactants, but I want N2 and O2 gas as products. So we're going to have to reverse this reaction. The second thing you notice is that I have a half coefficient of 1/2 in front of the N2, and I have 1/2 in front of oxygen. I want ones in front of N2 and O2. So we're going to have to multiply this equation by 2 to get rid of the 1/2 and end up with ones as coefficients. So let's go ahead and do this. We're going to reverse the reaction. So NO gas on this side is going to go to 1/2 N2 gas plus 1/2 O2 gas. So we reverse the reaction, so that means we have to take the opposite sign. So the delta H so far for our new equation is going to be the negative of this. So this is going to be a negative 90.3 kilojoules. Okay, so the next thing we need to do is we need to multiply this equation by 2 to get rid of the halves so we can have 1 and 1 for our nitrogen oxygen just like they have here. So we're going to multiply everything by 2. So we're going to multiply this by 2. 1/2 multiplied by 2 is 1. 1/2 multiplied by 2 is 1. You don't have to write the ones, but I'm writing the ones anyway. So now I multiplied the equation by 2. So that means I have to multiply the delta H by 2 to get the new delta H. So we're going to multiply that by 2. Okay, so that's equation 1 is ready. What about reaction 2? So again, you'll notice we have chlorine gas as a reactant, but we want chlorine gas as a product. So we're going to have to reverse this. And also, again, notice it has a 1/2 coefficient. I want a 1 there. So again, we're going to have to multiply the equation by 2 to get rid of that 1/2 and end up with 1. So let's go ahead. So reaction 1 was changed to this one. And now reaction 2 is going to change. So we're going to reverse it. So we have NOCl. Notice that we have NOCl as a product, but we want that as a reactant. So we're going to have to reverse this reaction. So NOCl gas becomes NO gas plus 1/2 Cl2 gas. Okay, so we reversed the reaction. So this is going down here. We reversed it. So now we're going to have to take the opposite sign here. This is a negative 38.6 kilojoules. So this is the delta H of this new reaction is going to be equal to the positive value of that. So positive 38.6 kilojoules. Okay, so we got it reversed. So next thing we need to do is multiply the equation by 2 to get rid of this 1/2. So we're going to multiply this by 2. We're going to multiply this by 2. And we're going to multiply this by 2. And that's going to give us a 1. And so now we're ready. So again, since we multiplied our equation by 2, we're going to have to multiply the delta H by 2. So that's going to be multiplied by 2. And let's see what we get here. So notice that we have NO here, 2NO. We don't have any NO in our target equation, so we're hoping that this cancels out, and it does. So you'll notice that I have 2NO here, and I have 2NO as a product here. So here's its reactant, here's a product. When I add these together, they're going to cancel out. So that's going to cancel out. And for the rest of it, you can see that I want 2NOCl for my target. Here I have 2NOCl gas. And I have one, I want one of each of those. and you'll see that I have one NO2 gas, one O2 gas, and one Cl2 gas. So when I add these together, I get my resulting equation. So my resulting equation is 2 NOCl gas goes to N2 gas plus O2 gas plus Cl2 gas. So to get the delta H of my resulting equation, I add these together here. So I multiply this by 2, I multiply this by 2, and I add together, and I get the final delta H of my new reaction is equal to negative 103.4 kilojoules. So that, ladies and gentlemen, is how you calculate the heat of a reaction using those relationships between the delta H's and their equations, and using Hess's law to add up your equations to get the final delta H or heat of a reaction. So I hope this was helpful. I hope this clarified anything for you. If you enjoyed this video and learned from it, please share this video, like this video, hit that like button right there. Also, hit the notification bell so you can be notified by other videos that I put out, all my videos. Subscribe to my channel. Also, put a comment down in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.